All right, topics of math, 4.3, vocabulary and representations of graphs. Graphs are used for social science, computer science, chemistry, biology, transportation, and communications. The vertices can represent the objects, and the edges will represent a relationship between those objects. A connected graph is a graph where there is at least one edge to each vertex. Okay? And then adjacent vertices. Adjacent, if you think I can think of in geometry, adjacent angles, that means they're right next to each other. But this one has to be a little bit more specific because just because D and E are right next to each other doesn't mean they're adjacent vertices. They also have to be connected. They need to share an edge. Okay, so what vertices are adjacent to A? So which ones are connected to A is what we're really looking for. So A would be B and D and E, all three of these lines. Okay, so then go to the next one. Which vertices are adjacent to B? So again, even though D and E are kind of right there across, they're not adjacent, they're not next to B or connected to B. So we need to only choose the two that are connected to B. So A and C. All right, why don't you do C, D, and E? See what you come up with. All right, so C would be B, D, and E. D would be just A and C, and E is just A and C. Draw a graph with 5 vertices where every vertex is adjacent to every other vertex. All right, so let's go ahead and put some dots out. 5 dots to represent your 5 vertices. If you want to name them, you can, or you can just make them dots. And then what we want to do is connect each of these dots to each other. So if I take this first dot up at the top, I want to connect it to all the other dots, all the other vertices. Okay, and then start at, so I'm thinking like, if you're thinking that's maybe my A, we could have this one be my B. Now start at B and do the same thing. So we already did A to B, we don't need to do that one again. So just jump like B to C, B to D, B to E. Go ahead and finish up this graph. Pause the video and finish up this graph. Okay, so it should look something like this, where you have every vertex connected to all of the other vertices. This is called a complete graph. Okay, so what we've made, since everything is connected, we say it's called a complete graph. Our graph can be described as K sub n, where n is the number of vertices, so ours would be K sub 5. Okay? All right, let's try the next idea. 2 other ways to represent a graph. We can list the set of vertices and the set of edges. So we'll go like vertices equals, and then just list out however many vertices there are. In our case, there was 5. And then we can list out the edges. So this will be like 2 letters. What 2 vertices are connected, and so on. So we'll practice this here in just a minute. And then the last thing, we can use an adjacency matrix. All right, list the set of vertices and edges. So this is a different graph than the one we just made, our complete graph. This one is not a complete graph. Okay, so if I want to list those vertices, I'm going to list V equals, and then just list out all your points. So we have A, B, C, D, and E. Okay, for the edges, you don't need to repeat it forward and backward. Like if you already wrote down AB, you don't need to write down BA. So we have AB. I like to just start with the same letter. So AB, I'm going to do AC and AD. So those are the 3 edges that start at A. So now I'm going to go look at the edges that start at B. Okay, I already did BA because that was the same as AB. So I'm going to go BD, and that's it. Okay, we already have the other one, BAAB, so we're just going to add BD. All right, so now I'm just going to jump to C. So again, we already did CA, so I don't need to list that one out. It's already written right there. So now I'm going to go from C to D and C to E. All right, so then go ahead and start with D. So we already listed DA, we already listed DB, we already listed DC, because that's the same thing as CD. So the only one we have left was DE. Okay. All right, next thing, make an adjacency matrix. So what this is going to do, you're going to list out all your vertices kind of in a matrix. So like A, B, C, D, E on the top and A, B, C, D, E going down the side. And we're going to make a matrix out of it. So what we're going to put in this matrix is a 1 if they were connected and a 0 if they weren't connected. So in a little bit, we'll figure out how could A possibly be connected to A. It actually can, but we're not going to do that one quite yet. So we're going to say A is not connected to A, 0. But A is connected to B, 1. So I can go AB is 1, and then BA is also 1. Okay, A is connected to C. So AC has a 1, and then CA has a 1. A is connected to D. So AD, AD. A is not connected to E. There's no line that connects A and E. So we're going to put a 0. All right, let's start with B. Okay, B is connected to A. We already did that one. And B is connected to D. So BD has a 1. All the rest of them have zeros because B wasn't connected to B, B wasn't connected to C, and B wasn't connected to D. But BD should be a connection, and then also DB. So that one should also work. Okay, but BC was not, BE was not. All right, so let's go to C. So we have CA, CD, and CE. So I already did A and B. So now we need to do C is not connected to C, C is connected to D, and C is connected to E. So D and E, yes. All right, why don't you finish up those last 4 numbers? How many zeros, how many ones? So starting at D and E. So go ahead and pause the video and try those last couple. All right, so should have gotten 0, 1, 1, 0. Okay, D and E were connected, but D wasn't connected to itself and E wasn't connected to itself. So then another thing we're going to do is actually just add up these rows. This will tell us how many vertices are coming from A. So A, we add that up and we get a 3. B, we get a 2. C, we get a 3. D, we get a 4. And E, we get a 2. We could also figure this out by, let's just take this D example here. We got 4. Well, if I go up to the D line up here, 1, 2, 3, 4. So it's how many edges are coming from D. Okay? All right. I'm going to do something else with this. So using that same example we were just using, degree of valence is the number of edges that have a vertex as the endpoint. So we write degree, and then in parentheses we write vertex. So the degree of A. So since A had 3 lines coming from it, the degree of A was 3. Since B, you can look at that matrix we just made, B had 2 lines coming from it, so the degree of B was 2. The degree of C would have been 3. The degree of D was 4, and the degree of E was 2. Okay, so again, to figure out the degree of valence, we can, in our adjacency matrix, we can find the sum of each row. So just add up those numbers in each row. All right, one more idea here, that loop. Okay, so if an edge, or if a vertex can actually connect to itself, so let's say I had the points A and B, vertices A and B. So normally it might have A connected to B, but you could also have A connected to A. So it's just going to make kind of look like a loop, a circle there. So when you want to count how many edges are coming from A, we actually need to count this twice. So we have an edge coming from here, you have an edge coming from here, and you have an edge coming from here. So to actually be like 3 edges coming from A. Okay, so that's that loop idea. Also, we could have 2 lines that connect A and B. So we could have A and B connected like this, and we could have A and B connected like this. You could even have 3. This is called a multigraph. Okay? All right, let's try the next example. Find the degree of each vertex. So what you want to do is start at A and figure out how many lines are coming from A. So we had 1 here, there's 1, there's 2, there's 3, and there's 4. So the degree A actually had 4 lines coming from it. So we're going to say 4. Okay, B had 1, 2, 3, 4. C, 1, 2, 3. D, 1, 2, 3. And E, this is the one with that loop again. We've got 1 here, 2, 3, and 4. So even though it comes back to the beginning, you have to count it as 2. So we're going to say 4. Okay, so make an adjacency matrix. So that's where we're going to write out our A, B, C, D, and E, whatever the names of your vertices are. And then see if they're connected. Now again, if you have that loop, does A connect to A? So we have to count that as 2. A connects to A twice because it has the starting spot over here and then another starting spot over here. Okay, so now does A connect to B? Yep, 1 time A connected to B. So that means B connected to A. Did A connect to C? This one's a little bit hard to see. If A connected to C, because it goes through B, but it doesn't actually directly connect to C. Okay, so we're going to say 0. A does not connect to C. Okay, D, does A connect to D? Yep, 1 time. And then how about E? Does A connect to E? Nope. So again, 0. Okay, then we go to B. Does B connect to B? So did B have that loop? It did not have that loop, so B does not connect to B. Okay, B to C, yep, 1 time. B to D. B did not have a direct connection to D, so nope. And then B to E. Now this one actually is that multigraph because B to E goes here and then B to E also goes here. So how many times did B connect to E? 2 times. All right, see if you can finish this up. Go ahead and pause your video. All right, so if you finish it up, go ahead and check those. Remember, if you have that loop, that's going to count as 2 connections. All right, so then your assignment is page 185, numbers 1 through 3, 5, 6, 7A, 8A, 9, and 10. Let me know if you guys need anything. Take care.